this webinar series. And first of all, thank all of you for attending this TFTC webinar series from the theme of ISTTT 21. And I appreciate your attendance, given that this might not be the most convenient time for you. Particularly, we have audience from all over the places around the globe. So I really appreciate your attendance. So I want to thank Dr. Jack Haddad and his lab for the sponsorship to this GoToWebinar platform. And I want to thank Dr. Jorge Lava for his help with the organization, and also my graduate students, Mose and Passerfeld, for his facilitation on the technological issues. First of all, I would like to ask the audience, except the speaker, to mute yourself most of the time, unless you want to speak out. It's very easy to mute yourself. Just to click the microphone icon on the ribbon on the left, and you're going to toggle on and off the audio system. So it'll just minimize the background noise. So we will have a presentation around 40 to 45 minutes, and you'll be able to ask questions in the remaining time. So this this session is recorded, so now I've already clicked the recording buttons. Everything will be on record. Just to follow those who cannot attend this as webinar, they can watch offline later. So today we're very happy to have a young talented scholar, Dr. Jiwon Kim, and she's been an assistant professor in the School of Civil Engineering, the University of Queensland, since June 2014. She received her PhD in Transportation Systems Analysis and Planning from the Northwestern University in 2014. For her thesis, Travel Time Reliability of Traffic Networks, Characterization, Modeling, in a Scenario-Based Simulation. Dr. Kim's research is broadly in the area of modeling and analysis on urban transportation systems, with an emphasis on the application of traffic flow theory, data mining, and predictive analytics for effective traffic control and congestion management. Her current research focuses on spatial temporal trajectory data mining, which aims to leverage massive amounts of movement data generated from GPS and mobile sensors in urban spaces to better understand vehicle and passenger mobility patterns and predict the trends and anomalies in dynamic traffic flow and traveler behavior and network performance. Dr. Kim was awarded the 2011 Green Shield Prize by the TFT committee, which is a hosting committee for this webinar series. And she also received the Best Paper Award from Transportation Network Modeling Committee, TRB, and Ruichi Kitamura Best Paper Award from ADB 00 from TRB in 2014. And I personally enjoyed a number of her presentations at TRB and other conferences. So, so let's thank Dr. Kim for her contribution to this webinar series. Without further ado, I'll give the stage to Dr. Kim. So welcome, Dr. Kim.
Okay, hello. Thank you very much. Thank you for the introduction. And thank you everybody to join the webinar. Yes, this work has been presented as in the ISTTT 21 series, and this work has been done by myself and my PhD advisor, Professor Hanima Masani at Northwestern University. And I also would like to recognize the Strategic Highway Research Program Chart 2 project, which supported this this overall paper work. So, okay. So let me start with the motivation and the resources of this paper, and everything actually started from having this large amount of trajectory data, who is currently now becoming more increasingly available. But at the time that this study has been done, that there are not many the data set that cover this entire network, entire city area. So the motivation was to have a systematic approach to mine trajectory data, so that we can get some insights and have a more automatic way of discovering the useful and interesting patterns from data. So the trajectory data is just a sequence of consecutive georeferenced coordinates, latitude and longitude coordinates, and these associated timestamps. So this has been now collected from various GPS devices and mobile sensors. And the real advantage of this data is just its comprehensiveness and its ability to cover, telling us a lot of the information about the moving objects. So it gives a travel time information and partial or full trip information, and also very detailed speed profile, acceleration and deceleration profile across their journey, and the route choice information, the information of travelers can be also extracted. And from this network-wide, we can extract origin-destination trip patterns and also city-wide traffic dynamics patterns. So it gives the combination of both micro and macroscopic information. So the availability of this vehicle trajectory data has really opened up new opportunities for a more comprehensive and network-wide and city-wide analysis for transportation researchers. But there exist a lot of challenges in dealing with this vehicle trajectory data. The first one would be its huge volume and massive size of those data, and it has been collected in very fine resolution, maybe 1 point in seconds. So it really quickly grow in terms of volume. And with this high resolution of data, there are a lot of noises, and also it includes information about both spatial and temporal dimensions. So properly applying these information and extracting information from the data is quite challenging. So there is a research need to use those trajectory data in our research, but it requires more technical methodology and systematic methodology that we can really use to extract data more, the information more in an effective way. So this study focuses on trajectory clustering method, which is just a basic step for mining trajectory data. So trajectory clustering is to automatically cluster similar trajectory together into the separate groups in order to identify spatial and also spatial temporal patterns. So the overall objective and contribution of this paper is that the main goal of this paper is to apply the data mining techniques, specifically trajectory clustering methods, to find and visualize natural groupings and patterns in vehicle trajectory data set in an unsupervised manner. And the contribution of this paper is the development of systematic framework for clustering and also classifying vehicle trajectory data, and they can be applied to a wide range of trajectory data sets because it does not require pre-processing called map matching process, and it can be used without having this underlying road network information. And we can cluster trajectory into both just a spatial dimension or spatial temporal clusters, but this paper particularly focuses on this discovery of spatial clusters in the network-wide manner. So there is a lot of existing trajectory clustering methods. In early stages, the trajectory mining clustering method has been applied to the freely moving objects such as animals and hurricanes, and the algorithm called TrackClus was the most widely used the clustering method in the early stages of study. And then in the transportation domain, there's been a number of trajectory mining, trajectory clustering method has been developed, and focusing and recognizing the fact that the trajectories, vehicle trajectories are actually constrained by the network. So the net scan and then cluster and need, those are the number of clustering methods that cluster network constrain the trajectories based on their underlying network information. And with this existing methodology, the aim of this study is to cluster trajectories, but without having to have a pre-processing procedure. So our aim was to really purely work on these trajectory data sets only. And also another goal was to take into account some different characteristics of the vehicle trajectory. It can have a different length, and it can have a different points, sampling points, and different uneven sampling rates. And we should be able to recognize different directions and locations, and those sort of flexible characteristics should be covered in clustering methods. But even though we don't consider this network information in our clustering method, because trajectory itself is just really constrained by road network, our method uses this knowledge that trajectory can quite quite heavily overlapping when they use the same route or same path. So the trajectory is denoted in TR in this paper, and the points in trajectory is noted in this P. So we're going to have 1 to n point in this direction, and we use this notation. So in any clustering method, it requires two different information. One is how you define similarity measures for your objects to cluster, and what kind of clustering algorithm should be used. And in our methodology, we use similarity measure in terms of longest common subsequence, and in terms of clustering algorithm, we use density-based clustering called DBSCAN. And the longest common subsequence is to identify the longest overlapping portion between these trajectories. And this is based on the idea that the extent to which vehicles' route overlap indicates their similarity in terms of their level of closeness and spatial closeness, and also relatedness, as well as potential interactions between these vehicles. So although we are not trying to cluster this vehicle into this spatial temporal dimension, even if we just cluster trajectories into just based on their spatial similarity, but still vehicle can use this road in any time of day, and there will be some kind of level of interaction that can affect each other by just using the same routes and same spatial region. So that was the basic idea, and this clustering framework has the 4 different stages. So first step is to define similarity measurement. So once we measure similarity, then we obtain this distance metrics between these pairwise trajectories. And then once we have distance metrics, then we use this distance metrics to cluster trajectories. And with the set of clusters, we define this representative sequence that represent the spatial clusters, which called the Cluster Representative Subsequences. And this can be used to represent a spatial region, and also can be used to classify trajectories when there's a new trajectory coming. So these are our overall steps and framework of our methodology. So the first step is similarity measurement. So what is longest common subsequence? So this is an algorithm and method to find this longest common subsequence of 2 sequences, and it originated in the field of string matching. And so if you can see here, and that was the string, one string sequence and another string sequence, and the longest subsequence between these 2 string sequences to match the first and the last common component together, so that we can have what is the longest subsequence that have been matched across these 2 sequences. And from this idea, this has been widely now used to time series clustering, where each element can be just point in time in the time series. And then later, this has been applied in spatial trajectory data as well. So that's where we are using this longest subsequent common subsequent in this trajectory analysis. And there's a couple of advantages of this longest common subsequent. And there are different similarity measure that has been used in trajectory data. One is Euclidean distance, which is shown in the first figure. This red line shows this one trajectory, and the blue line shows another trajectory. And the Euclidean distance tries to measure the distance, just a straight distance between these points. Okay? But this is quite sensitive to distortion. So the Euclidean distance has been have a disadvantage in that sense. And another similarity measure that is widely used is dynamic time warping, which is shown in the second part. And this can be a little bit, is much less sensitive to this distortion because it allows to match these points without complete overlap, but it just can recognize something, the best alignment within this this shifting and distorting manner. So, but the one drawback of this dynamic time warping is that you have to match every point in this sequence. So in this case, one has to be matched at least others. So it is a little bit sensitive to noise. When you have some deviation from your main path, something like here, maybe you might want to skip this part because in our travel pattern trajectory, it might be the case where somebody has just used some non-usual route and it's not actually characterized their own usual routes, but the dynamic time warping will consider all those deviated points into account when they're measuring the similarity. So this is a little bit sensitive to that kind of deviation. And longest common subsequent does not have that problem because it doesn't require matching every point in this trajectory. So if it is too far from matching point, it can be just skipped. So that is some quite strong, powerful advantage of this longest based similarity measure when this is used as the trajectory data. So we defined point similarity measure first in order to match the points pairs in the trajectory. So every point in this trajectory and every pairwise these points between this trajectory has to be measured in terms of its distance. So this is what we define as a sim point. It's a similarity between points. So for example, here point 2 and point 2 in I and J has a similarity measure denoted as a 0.8, and similarity measure between second and third points is 0.6 and so on. So how it is measured? So this is the equation formula that we used to define this similarity measure between point pairs. So when point 1 and 2 are provided, then we just directly measure Euclidean distance between 2 points, which is this point here, and this is Euclidean distance between these 2 points. And if this 2 points distance is greater than some threshold value, delta, then we consider the similarity between 2 points is 0. And otherwise, we use this formula to measure the similarity. So similarity measure can be between 0 and 1. And whenever the similarity has non-zero sim point, then we think it is matched. So it can be matched with real 1, or it can be a match with a 0.2. But as long as it is has a non-zero value, we consider it as a match. Okay. So with this similarity measure between points, we now find longest common subsequent using this dynamic programming algorithm. And this is a already very known algorithm for finding longest common subsequent, but we have a little bit of modifications in traditional longest subsequent algorithm. So one specific modification and extension is that in existing method, once it finds a particular match, it does not try to further search for a better match for a given point. For example, in this first trajectory and third point, it has 3 non-zero matches in the opposite, the other trajectory. So 3, 4, 5 are all matched with this 3. But in the existing method, if it finds the match, for example, here first, P3, then it will just try to consider this and this as a best alignment, and it does not try to find further the better match with this point. But in our case, if you can see these two pictures, apparently the 4.4 is a better match because it's much closest to P3. And in the second picture, this 0.5 is a better match because it is the closest one. It has the highest similarity measure. So in order to distinguish that sort of the actual distance between points, we a little bit modify and use this modified score function. So in searching for this match, we try to find largest of the 3 components, and I'm going to give a small example to how we use this algorithm to match the find longest common subsequence. So this is quite the standard way of finding longest subsequent measure, and this type of algorithm can be found in various places. But I just want to show that there is some difference between existing method and our method by showing that we can distinguish LCS between these two cases. So we create some table where these rows shows these points in the first trajectory, and then columns shows in the points in the second trajectory. And we add this zeros value just for the algorithmic purposes. And then each cell, we write down this similarity point, the point measure between the pairwise point, and the calculated score, LCS, which is defined in the previous slides. So we initialize by just setting all 0 on the 0th line and 0th row and column using this. And the second, for a given row, which is for the first point in the trajectory, we compare this similarity measure between point pair for all points in the other trajectory. So for example, if point 1, compare the point 1 and point 1 here, and this is there's a no match. If you have a number here, that means it has a non-zero similarity measure. But if you don't have the number, that means it is just 0, or it is it cannot be matched. So when it is not matched, we just set this 0 value here. And for the second case, it's the same. For the first pair, there's no matched points, so we just all write down this 0 here. And then we go to the next point in the trajectory 1 and trying to find this match between this point 2 and the other in the other trajectory. And for example, in the point 2 and point 1, there's no match, so it will write 0 here. And then point 2 and point 2, there's a match, so point 2 and point 2 are now matched. And we will there's a similarity point, which is a number here, can be written in this cell. And then the number in parentheses is this calculated cumulative score LCS. So we compare this cumulative LCS score from this previous cell plus its similarity measure and this adjacent cell. And the largest the number score LCS would be 0 plus 8.8. So we define this score from LCS as 0.8. And then we compare this second and third point, where it is also matched with the similarity measure of 0.6. So we write down this 0.6 here. And then in terms of defining score LCS, we try to compare 3 cases where 0 plus 0.6 or this cumulative score measure from this just next cell or this above cell. And among these 3, we find the just left cell has the largest one. So we write down, we just have pass this value to here and then indicate that arrow, left arrow, showing that this cumulative score has been coming from this left cell. And then if you compare this 2 and 4, and there is no match, so we will just have a 0, 0. And similarly, in the second case, because it's just the same, so we will have the same number in the cells. And when we compare this third and this fourth row, now compare this third point and then the other points, and all are the same until this point. So when we compare this third point in I trajectory and third point in J trajectory, it shows that similarity measure is 0.4. So we say that's a 0.4. And then when we calculate the score LCS, we compare 3. One is cumulative score LCS from this left top cell plus its own similarity measure. So 0.8 plus 0.4, or this score LCS from left cell, score LCS from top. Among these 3, the sum of the top left score plus its own similarity measure is the largest, which is, it will become 1.2. So we will take this one as our LCS score, and then we will indicate that arrow saying that this value is coming from left top cell. And then when we compare third and fourth point, it has its own similarity measure, which is 0.9. And when we calculate the score LCS, we also now trying to compare 3 components, 0.8 plus 0.9, which is 1.7, or this score from left cell, score from above cell. So between 0.2, 1.2, 1.7, 0.8, we find that this is the largest. So we take this as a score LCS, and then we indicate that this one has been coming from this left top cell. So we are repeating this procedure in all cells, and then finally, this is actually the same. So finally, we fill all those new cells, and then we can now track back to identify the LCS part. So starting from this last cell, we follow this direction indicated by this arrow. So for example, here you can either go up or left. And if you go up, and then it says that it goes left. So, and then it goes top, left and top. So this shows that how you can track down and then find this matched point here. So whenever you have this upper left arrow, that's where your matching point were found. So in 2 different cases, this first case, we found this matching point between 2,2 and 3,4, which is here. And then second case, we found this this upper left arrow found in between 2,2 and 3,5, which is here. So now we can say that these 2 are matched, and between the cell, which is 2,3,4 and 2,3, these shows the subsequence that are considered to be overlapped, which is a character defined by LCS. And with this similarity, our dynamic programming, you can see that we find the different this matching and LCS subsequent results. So this one was identified. It can be identified from the very small example. So once you identify the best, the LCS, longest subsequent sequence measure for all pairwise trajectory, then now we can measure similarity, finally measure similarity between trajectories. So assuming that every pair of trajectory, we have this LCS calculated, and then we define similarity between two full trajectory as follows. So if this smallest overlapping portion, which is LCS length, is less than some gamma value, which represents the minimum required length for being a valid LCS portion. If this is a smaller than, shorter than that, we just assume that similarity between these two full trajectories is 0. And if it is greater than 0, then we define the similarity of sequence as the LCS of the length of this LCS divided by the minimum, the length of the shorter trajectory. So, and in defining this length of LCS, in traditional approach, if you have the metric point 3, then in traditional way, the length of LCS was calculated in terms of cardinality. So no matter how far this matching point apart each other, you will see that this is a 3 matches, and the cardinality is 3, because it is coming from the string matching problem. So it doesn't recognize difference between these two cases where both have a 3 matches between these two trajectories if we apply this traditional string matching algorithm. But in our trajectory data set, these have a very big difference because sometimes the sampling rate can be quite different. So instead of using this cardinality, we use actual distance covered by this entire longest common subsequence. So that's where we can interpret longest subsequent measure in terms of overlapping route and overlapping travel distance. So there's some example of calculating this longest subsequent measure. This S is a similarity of sequence where we have 6 different cases that was provided as an example. So as I mentioned, this similarity measure is just length of LCS between two sequence X and Y, ratio between this length of LCS to minimum length between X or Y. So for example, if you look at this first example, and this circle and triangle shows origin point of these two trajectories, and it has 0.63, means that it has an overlapping portion which accounts for 63% of this shorter trajectory, which is a blue one. And if you look at this B example, and this has an overlapping this has a merging and diverging. So this 30% of overlapping has been identified. And if this is a shorter trajectory completely overlapped within a longer trajectory, then it is, because it is based on shorter trajectory length, it can be almost 1 or something very close to 1. And the D is the case of where you have a merging and diverging, and we identify that the median point of overlapping. And you can have a different origin point where this origin started from the some part of this trajectory. And in this case, the final case is similarity 0, because although there has been overlapping portion, but it's a different direction. So identifying this subsequence is useful when you have to distinguish between different directions. So, yes, this is an example. So once we identified and calculated the similarity measure between all pairwise trajectories, then we can cluster trajectory into similar groups. So we use density-based clustering method, which is the very popular clustering method, and it originally has been applied in this point data, which is shown in this figure, but there are many applications applied this into different type of data sets, such as trajectory data set. So density-based clustering method requires 2 different parameters. One is epsilon, that represents the maximum radius or distance for being a neighbor of a particular point. And then mean trajectory is the minimum number of trajectories required to become a significant cluster. So algorithm works in the following way. So starting from an arbitrary trajectory point, we check if this has a sufficient number of neighbors by checking its absolute distance boundary. And if it has the number of trajectory neighbor that is greater than this minimum required number, which is mean trajectory, then it can start forming a cluster. And then we try to expand this cluster into by adding other neighbors, neighbors, and neighbors, and so on until it doesn't have any significant neighbors. So using this methodology, we had a number of experiments to identify the effect of these parameters in trajectory clustering results. And as you can see that the choice of absolute and minimum trajectory actually have a quite different impact on the final cluster results. Roughly speaking, the smaller epsilon, the larger mean trajectory, mean TRS, the stricter the requirement to form a cluster is. That means we will have less and smaller cluster to be formed. So, for example, in the first row, the first column shows the cluster trajectories, and the second column shows the just representative points or the most dense part of these trajectory clusters. And first case was with the epsilon value of 0.2 and mean trajectory is 10. And compared to this, the second one was we increased both epsilon and mean trajectories and up to this point. As you can see that as the epsilon value increases, it has a less restrict. So it requires that the epsilon of 0.2 means that you require at least 80% of your travel route should be overlapped by other trajectory in order to be considered as a neighbor in defining epsilon neighbor. And the mean trajectory 10 means that you need to have at least 10 such trajectory in order to form a cluster. And by increasing this epsilon value, we are a little bit relaxing our constraints. So you can, for example, 0.9 means that you can just have only 10% overlapping. But at the same time, by increasing this number of trajectories, so that means, which means you will have to have 27 such trajectories to form a cluster. You can have some balance in creating different type of trajectories. And so the insights from this kind of clustering algorithm using this density-based algorithm is as follows. It's summarized as follows. So all trajectories in a cluster share a significant portion of their routes with at least one other trajectory in the cluster, and specifically the length of the overlapping portion, which is characterized as this LCS part, should be greater than this 1 minus epsilon times in terms of percentage. So this is the same as I'm saying that this 0.2 means that you have to have overlap 80% of your shorter length, percent of your route. And the core trajectory, which is a trajectory that has their neighbor that the greater than the mean trajectory number, is sharing their routes with that specified, at least that specified the parameter number. So if we say this mean trajectory is at 10, that means core trajectories in that cluster have shared their routes with at least 10 other trajectories along their journeys, not particularly at the same time point, but there has at least a mean trajectory, other trajectory that use the same routes within that cluster. And all trajectories within the cluster are somewhat connected through the chain of LCS. And also, as I mentioned, two vehicles in the same cluster could possibly affect each other, although they are not concurrently moving together. But with a small time lag, it can be affected each other by just the propagation and traffic flow, or assuming that any vehicle who use this route can use this route in any time of the day. So we can assume that there's some interaction between these cluster members. So there's been some discussion in the choice of epsilon and mean trajectory in the paper, and I would like to just summarize some insight about this, how we can choose these two combinations, the combinations of these parameters. So large epsilon and large mean trajectory produces loosely connected big traffic streams cluster, which was shown in the bottom part of the picture in the just the two slides ahead, if you remember. For example, in this case, this the lowest part is the larger epsilon and the larger mean trajectory, and then upper part is the smaller both parameters. So when you have a large epsilon and large trajectory, mean trajectory, you tend to produce very loosely connected big trajectory stream cluster, and a cluster tends to have a very large spatial coverage, and this can be used to provide insight into how far a particular chain of connected trajectories can reach, and applications of this might be information these vehicle-to-vehicle communication or information the modeling, how far a particular route, the trajectory can affect each other through their chain of overlapping route portions. And when we use the small epsilon and small mean trajectory, it should tend to produce a very tightly connected, heavily overlapped small stream. And this cluster tends to be very locally concentrated, so we can identify just the number of trajectories that are really truly close in space, and which are in many sense quite useful in identifying in terms of actual clustering and the spatial clustering. And identifying some type of bottleneck area, this kind of small choice can be quite useful. So defining the cluster parameter should be based on this purpose of analysis. And
hey, Jiwon.
Yes.
Yeah, I'm sorry for chiming in. There is a question coming up on the chat box. Do you want to address it now or leave it to the end? It's up to you.
Okay, let me check. I haven't. Okay, let me check.
Yeah, you have a chat box.
Okay, so what are the typical number of points in a given trajectory? It depends on the trajectory data, and if we use this GPS trajectory data, it can be just 1 point at a second, so it can be a quite large number. But if we use this passenger trajectory data collected from bus passenger, then each point represents bus stop, so it can be less than 10 for one trajectory. So, so we don't really specify the particular trajectory data set, but just any sequence of trajectory points are currently addressed in this study. So it can be very large and computationally quite expensive if you have a very, very large number of data included in the trajectory. Okay. So the cluster representative subsequence is to understand some representative points and segments based on overlapping portion. So this is a schematic diagram that how we can measure it. So each LCS portion can be considered as an intersection between two pairwise trajectory, and then we take the union of those LCS together to identify the overall the common part of that this trajectory members. So in doing so, we use a hierarchical agglomerative clustering method. So the case study has been conducted using the TomTom GPS data, and the overall data set was collected from 2 weeks in 2010 and approximately 10,000 trajectories per day. And we used to train our identify this cluster using 10 trajectories between 8 a.m. to 6 a.m. to 8 p.m. from Tuesday weekday in May. So this is a result of this cluster analysis. So we take the combination of 0.4 and minimum trajectory of 14, and we identified 5 different spatial clusters, which shown in here. And from this direction, it was quite interesting that the cluster 1 and cluster 2 has a quite similar spatial coverage, but its direction is opposite. And cluster 3 and 4 is the same, so you have a quite similar spatial region, but it's the direction is different. And then cluster 5 is where you have the expressway of the Long Island area, and usually a lot of traffic coming from this outside to this city area. So the overall cluster result was quite consistent with the understanding of this region. And when we overlap all together, it just really overlap. It doesn't really give an information, but when you cluster into these different groups, then you can see that there's a layers traffic stream that actually behave differently, and that can be used to analyze some cluster-specific traffic analysis. Traditionally, we have been applying our traffic analysis method for particular area, particular link, or particular OD pairs, but now with this clustering results, we can try to characterize actually layers traffic flow, and we can identify the characterized properties for different traffic stream and traffic flow groups. Okay, so we did a very simple experiment about how we can use this spatial clustering for the further analysis. One application can be testing the assumption that different spatial cluster might have different temporal behavior. So we try to group the spatial cluster, spatial trajectories into different daily group. So just using this K means clustering, we set this K equal 2 so that just Monday to Sunday, we can try to identify these different trajectory cluster to different day groups. And we discovered that from cluster 1, there is a distinction has been made between Sunday and then the other day group covered all Monday to Saturday. And then for cluster 2, a day group has been clustered into this Monday and the Tuesday to Sunday forming another group. So it was a quite simple experiment, but it shows that there is the implication that different spatial cluster has a different temporal the profile, and when we do this clustering analysis, it has a quite benefit compared to we are trying to cluster this data into spatial temporal clustering. And when we do this spatial temporal clustering, it might be useful to identify real moving cluster or real the clustering pattern in both spatial and temporal dimensions. But when we want to sort of compare a particular these temporal patterns, we need to have some basis for comparing it. So cluster 1 is, cluster 2 is representing some different regions, and then we can compare their difference in their temporal patterns. So just focusing on spatial clustering is useful when you want to characterize and compare your temporal clustering patterns across different regions, across different the days. So this temporal traffic pattern analysis gives a very small example for that. And then currently we are applying this clustering method in different types of trajectory data. And one application that we are doing at the moment is to apply the clustering method into public transport passenger trajectory. And passenger trajectory data can be extracted from smart card data that has a tag on and tag off information. And by matching this tag on and tag off information with the underlying route information, we can extract and construct passenger trajectory data. And as I mentioned, in that case, each point would represent bus stops. So it would be very coarse trajectory, but we can still apply the same trajectory method to clustering. So the picture shown here shows that clustering result of this passenger trajectories. So this is the Brisbane area, and it has a clear central point, and then a lot of traffic has the direction will be inbound and outbound. And then the left picture that shows all the trajectory displayed together can be more visually distinguishable and visually informative when you do this clustering. And then you can see that there's a different, the trip stream that actually coming identified from this clustering. Okay. And another application of this clustering method would be when applying this clustering into this trajectory for a particular person for a long time. Because rather than clustering this trajectory across this cross-sectional, you can focus on one particular person and then have their trajectory over entire long-term period, and then you can cluster their long-term trajectories into different root clusters. And this is one example that we identified from this longitudinal clustering. So one person, one passenger had their long-term trajectory data, and this right side, it shows that all the bar shows the time, period of time that where you have a particular trajectory started and ended. And then we clustered these trajectories into different groups, and it identified 3 different the root clusters, and which is highlighted into different colors. So the same OD, between the same origin destination, the blue and red and green have a different cluster. And in this case, we did that. So the green shows that the cluster that has been coming the opposite direction, because it is in the morning you go the origin and destination, and in the afternoon you come back. So this is a completely different cluster. But within this time period, in the morning period, it also recognized 2 different clusters. And we found that this shows that this represents 2 different routes connecting to OD. And the temporal overall long-term pattern shows that the user changed their route from cluster 1 to cluster 2. And that means there has been some difference in routes. And we identified that the route cluster has a increasingly high travel time at some point. So I think this user had some transition time and then changed it to route 2 at a later time stage. So by clustering this longitudinal trajectory of a particular user's groups, it can be also used to understand their long-term behavior. So overall, the aim of this study was to really leverage the amount of the large set of the trajectory data that has been continuously collected in these days. So with this sensor and also a lot of Internet of Things technologies, now the trajectory data are really increasingly collected, and it gives a really important insight into traffic patterns in a larger scale. So especially transportation research, particularly traffic flow and network-wide traffic flow theory and research can be really beneficial by applying this advanced trajectory pattern mining application techniques in a specifically very large scale traffic data. So it can be used to modeling the citywide dynamics and also detecting profiling citywide traffic characteristics, and then later it can be used to detect anomalies if it is different from this identified profiles or regularities. Okay. So it calls for systematic research for discovering knowledge from trajectory data, and with that advanced technologies and domain-specific applications, we can really leverage this big data analysis, big data source, and it can be done by through this collaboration across different research communities who have been separately working on the trajectory data, which include transport, computer science, and database and geography. So our team at the University of Queensland are currently trying to form this collaborative research team to achieve this goal. Okay. So that was the end of my presentation. So if you have any question, I'll be happy to answer. So please feel free to ask questions. Thank you.
Thank you, Jiwon. Very interesting study and very nice presentation. So for audience, if you have questions, you may either unmute yourself right now and and speak out from your microphone, or you can use the chat box to send out your question. So when you use the chat box, please make sure that you send the message to organizers and panelists only. Again, please select the option of organizers and panelists only from the drop-down box. All right, so looks like you've already got a second question from Amir Ghazi, and third question.
Right. So in case of having high accurate GPS data for computational issues, do you think that it is possible to first sample the data and then use the method? Yes, absolutely. That's a quite efficient way of doing that. So clustering can be done with this quite a subsample of data, because we can reasonably assume that quite a particular time of day and also day of week, we can pretty much characterize this overall patterns of this network flow, because it's not very changing dramatically. Every day you will have a quite similar pattern. So with this randomly, systematically well-sampled data set can be still very effectively used to overcome that computational issue. Okay, and the third question was, can you explain a little bit about the color scheme in the slide to temporal result? Okay. So, yes. So this picture shows that the x-axis is the time of day, and then within this one cell, this y-axis is the number of cluster, number of vehicles, number of trajectories within that cluster, because we are doing this spatial clustering. So there will be the temporal profile, the number of vehicles that within that cluster can change over time. So it shows that how this cluster size evolve over time within a time of day. And then the different lines shows that different day. Okay, so I have number of lines that shows that one particular day your number of the cluster size changes following one line, and then another Monday your cluster size changes another line. So each line shows that for in second line, for example, Tuesday, your cluster for one line shows that your cluster one size changes following another line. So we have clustered this overall size change pattern into different day groups. So the color doesn't really tell us about what particular day group characteristic is, but it just to try to distinguish these days are this profile is quite different from this profile. So if you just combine all together, all 7 these cells together, we will have whole lines that across entire Monday to Sunday, and then we cluster those time series into 2 day groups, whether or not it is coming from which day we didn't know. And then after we close those time series, and we try to now organize in a way that in a time of different day of week cells, and we found that a lot of the line that has been clustered into one particular day cluster, which is the purple, are all come from Sunday. And then the other time series set that are clustered into another, the day group, has been all coming from Monday to Saturday. And we did the same thing for all cluster, and for cluster 2, it says that when we divide its time series into 2 groups, the one specific day group has been coming from Monday, and the other Tuesday to Sunday, the time series coming from this Tuesday, Sunday were clustered into quite similar daily profile. So that was what it actually tells us. And then to vehicle emissions, vehicle trajectory data contains the speed information. what can we do on the speed clustering to identify the impact of the impact LOS? So we can actually, it is quite flexible in identifying this, defining your match between 2 points. In this case, we define these 2 points to be matched when these 2 points are in the similar distance, but we can add the speed components. So these 2 points are matched when both the spatial location as well as speed at the moment would be the similar. Maybe at that time we are actually already taking into account, incorporating this temporal information. But anyway, in that way you can identify the trajectory who has the similar distance, who traveled the similar path with the similar speed. So if you identify in that sense, you can identify this overlapping portion that has a significantly low speed, and that will give you this trajectory group that has a quite trajectory group that has a quite that experienced a quite low speed. And I think that if you find that sort of groups that across the region, that region would have a quite problem in this speed, and also if you say the speed change, not the just lower speed, and speed change can be also identified by defining this LCS profile. So we can identify this regional traffic flow stream that has a quite a variation in speed in terms of similarity measure, and that can be also used to identify the trajectory cluster that has a high emission problem. So not only just speed level, but also speed variation can be used to define your similarity measure. Okay, you enable delta parameter as the described threshold in the similarity function. Are the results sensitive to that? Delta is the distance between two. This is not very sensitive because, as I mentioned, usually these trajectories are constrained by network. So 20 meters that means you are trying to match these two trajectory when these two trajectory pass between these 20 meters. But usually this road length is not very wider than 100 meters and so on, because it's not moving objects that freely movable across this Euclidean distance. So usually 20 meters can be quite reasonable, and even this or smaller value can still reasonably capture those matching points. This is because these trajectories are already constrained by this width of road network. And so what was the platform, operating system, RAM, CPU you used to implement the clustering process? How long did it take to get the result for 1,000 trajectory case? So this study actually has been used some different computers, so it's not quite, and overall, the most computationally expensive part is calculating LCS, because LCS requires the computation of all the pairwise trajectory. So if you have 1,000 trajectory, that means you have to calculate 1,000 times 1999 times and then so on. So it's quite computationally expensive. So this study doesn't really try to develop this efficient algorithm to reduce the computational time, but there is a way that you can reduce the computational time when calculating LCS by filtering out something that is completely far from each other in LCS computation. And because LCS computation requires you to match these two trajectories, but if you already know that these two trajectories are already far from each other, then you don't really need to compute that. And these can be identified using some pre-screening process based on spatial index. So there's a very different other techniques that can be used to improve this computation. So yes, that was the limitation. The LCS calculation was a parallel limitation, so we are trying to improve this efficiency of the algorithm by using some spatial indexing techniques. Okay. I think that that seems to be all.
Yeah. Yeah, that seems to be all. All right. Before we conclude the presentation, I also like to add one of the last question. Okay, looks like they really liked your answer, and you'll say thank you. So just a comment maybe for a future research. Maybe you've already started doing that. So so basic trajectory mining for trajectories, the basic trajectories have temporal and spatial states. And later people, I think, proposed the semantic trajectory mining methods that can be also applied to transportation, because you have land use information, you have different modes of transportation, right? You can always augment the dimensionality of the data to get more information out from the trajectories, and also have a deeper understanding about the city patterns. So maybe you've already done that, but yeah, that might be an interesting area to look at.
Yeah, that is a really good comment, because now as trajectory data have been collected from this people's mobile data, they have a very location information, their location of point of interest information. So that is very powerful in characterizing the identified clusters. So yes, that's definitely what we are actually trying to incorporate in the clustering method and pattern mining.
Okay, well, thank you for the answer. I really enjoyed the presentation, and again, thank you, Jiwon, for this very nice presentation and a very new, methodology in transportation domain, and very useful tools for us, and I learned a lot. And also, I want to thank all of you for being here, and our next seminar will be next Friday morning, 9:30 a.m. And with this, I thank all of you for being here, and I think the session's adjourned. Hope you all have a good weekend.
Thank you very much.
All right, thank you. Okay, bye-bye.